Welcome to the Road to 5G, brought to you by the Rogers Corporation. Today's topic, Power Amplifiers Part 2, Design Considerations for Management of Temperature Rise in Amplifiers used in 5G mobile infrastructure.
Hi, my name is Aguayo from Rogers Corporation. In this video, we're going to talk about material properties for high power applications, thermal management for 5G applications. We're going to start out talking about PCB materials for high power applications. We'll then continue on to conductor considerations for thermal rise control. And then we're going to talk in addition to other material solutions that Rogers has for thermal management. When we talk about high power applications, many engineers usually think about low loss tangent materials. But in reality, what we're here to talk about is how thermal conductivity is the most important property when selecting a material for high frequency, high power applications. We're going to show you some data that compares RT-Droid 5880, which is very, very low loss material, to some material that have higher loss tangent but have a much higher thermal conductivity. In doing so, we hope to guide you in a direction to selecting high thermal conductivity as a primary property when selecting materials. In the table here, we have various materials that designers will use for high power applications. Historically, many have used RT-Droid 5880 for aerospace and defense applications. Commercially, the products like the RO4250B, RO3003, TC350 have been used. In the last couple of years, Rogers introduced a product, RT-Droid 6035 HTC, mainly for military applications, but is starting to find application use in commercial markets. The purpose of this table here is to show how when we can compare dielectric constant and loss tangent, and how the insertion loss versus thermal conductivity, we can look at then the graph that compares how temperature increases for the various materials and how the insertion loss compares. So when we look at the graph, you can see the RT-Droid 5880 is a material that has the lowest insertion loss because of its low dielectric constant and loss tangent, but it actually has the highest temperature rise because its thermal conductivity is so low, 0.2. Now the RO4350 is a material with the highest dielectric constant and the higher loss tangent. And therefore has the highest insertion loss. But it does have slightly lower temperature rise versus the 5880. Focusing on materials like TC350 and the RT-Droid 6035 HTC, you can see here the benefits, the vast benefit, when one is looking at dielectric constant and loss tangent, but very high thermal conductivity values, and how low temperature rise. So hopefully here what we're showing you, the designer, is that as you focus on material need for high frequency, high power application, TC, thermal conductivity, is the most important property you should focus on first. Then we can look at loss tangent and dielectric constant. As electrical engineers, we tend to look at every problem and try to solve it electrically. We try to reduce temperature rise by use of low loss tangent. But in reality, loss tangent has minimal impact when you're already working with materials with low loss. Thermal conductivity is really the factor, as we showed in the previous tables, that will affect the generation of heat and therefore temperature rise. In this table here, in this graph, calculated, we have what temperature rise is for materials with various loss tangents based on a loss tangent of 001 all the way up to 004, while keeping all other parameters the same. You can see that when you have a very, very low loss tangent but a very low thermal conductivity, yes, indeed, at 0.2, there's more dispersion of the values based on the DF. But once you start getting to values around 0.6, 0.8, and 1, these are values that typically are commercially available in products today, you can see that loss tangent becomes irrelevant. And so at this point, selection of the thermal conductivity value that is the highest of any materials that typically have low loss tangents, less than 0.004, is important. So all that was calculated data. Now the important thing is, what is the actual measured values? In the end, when we sit down to make the selection, we want to have our values based on what we measured versus what we calculated. And that is what this next chart will show. Here we have actual measured data of various materials from Rogers. RT-Droid 6035 HTC, the RO4350B, and the RT-Droid 5880. And for comparison, we also have in there some traditional FR4 materials, epoxy glass. These were 50 ohm materials on 0.5 millimeter, 20 mil laminates, bare copper, and we measured the the temperature rise using equipment that we could graduate the power up to 20 watts, slightly above 20 watts, 20, 25 watts. You can see here the impact that thermal conductivity has actual measured compared to the various materials. As we said, RT-Durit 5880 is the material with the lowest dielectric constant and the lowest loss. The theoretical data that I presented in the previous slides, you can see here in measured values, which is the line, the green line, 0.23 degrees Celsius per watt of increase in temperature per input power. So you can see that is the one that has the highest of the low loss materials. The RO4350B, like in the table before, slightly below the 5880, and the RT-Durit 6035 HTC will show the maximum benefit of high temperature, high thermal conductivity with low temperature rise. Just for comparison, you can see how high FR4 materials will be when you're working in this environment at high temperature and high power, in this case at 1.9 gigahertz. So what do we have? Rogers has multiple materials that are considered high thermal conductivity, varying in degrees from dielectric constant of 3 to dielectric constants of even 3.6, of 6.15, I'm sorry, like 3006, RO3006. This is to reduce the size of some of the amplifiers for lower frequencies. So let's compare some of these values. On the left, we have the materials that are PTFE based, and on the right we have those that are thermoset based. PTFE materials, RO3003, RT-Durit 6035 HTC, are materials that are pure PTFE and ceramic. As we showed data before, the RT-Durit 6035 HTC is the material with the highest thermal conductivity of products that are offered by Rogers. The TC350, the TC600 are materials that, that have higher dielectric constant in the case of the TC600 and higher thermal conductivity for the TC series, but they're woven glass materials as well. The RO3003 is one product that has a dielectric constant of 3, so the benefit of dielectric constant of 3 helps in the area of thermal conductivity. When we look at the thermoset materials, we have valued materials with loss tangents of 004. That's what the yellow line shows, the values of the loss tangents, and thermal conductivities in the area of 0.6 to 0.7. So these are the various choices that we have, either in high dielectric constant like the 4360 G2 and TC350 and the RO3006 versus those with the lower dielectric constant. So these are the materials that we have to choose from when selecting materials for high power applications and thermal management. In addition to material properties like loss tangent and thermal conductivity, what else should a designer be looking at when selecting the right material for thermal management? Conductor losses are very important to control. Copper roughness in particular is an area that is important to understand because it will have an impact on temperature rise. What we're showing here is the RO4350B material with standard copper, which is the blue line, and low profile copper, which is the magenta line. You can see here the improvement on insertion loss when you're measuring the material here. In this case, this is 10 mil material of the 4350B in a microstrip mode. The improvement in insertion loss for a much smoother copper is vital for the RF engineer, as can be seen here measured all the way up to 40 to 50 gigahertz. But what does that actually mean in the sense of temperature rise, which is really what we're here to talk about? Well, how does that increase in insertion loss affect or impact temperature rise as measured in an IR scan? What we have here is measured value of the temperature rise of two traces, in this case operating at 3.3 gigahertz with 85 watts of power input, 50 ohm microstrip line. You see the RO4350B standard material with the higher conductor roughness on the top, the standard copper, and then you see in the bottom graph you see the RO4350B low pro using the low profile copper. You can see here that the temperature rise that happens in these traces, there's a difference of about 15 degrees Celsius due to solely the impact of the roughness of copper. What this really is showing you is that in addition to thermal conductivity, RF designers that wish to manage better thermal management, temperature increases, should also be focused on using as smooth a copper as possible. In addition, designers have the option to work with metal plates to take away the heat. PCB materials, PCB circuit boards typically have values of thermal conductivity in the area of 0.5 to 1.5. This is not enough to drive the heat directly off of the device. So to do so, what you want to do is adhere the circuit board onto a metal plate, either by direct from the suppliers, or sometimes you use adhesive systems to do so. Rogers has a material that we can do that. Rogers product CoolSpan It's an adhesive system, a thermal electrically conductive adhesive system that will allow you to adhere a circuit board to a metal plate to be able to drive that heat out much higher levels. You can see thermal conductivity value in the range of 6 watts per meter per degree Kelvin, as compared to, as I said, values of 0.5 to 1.5 for PCB materials. Typically available in 2 to 4 mil thicknesses, you can adhere then the ground plane of the circuit board onto a metal surface like an aluminum surface to drive away the heat. So as we covered in this series here, electrical engineers, we tend to want to solve things electrically, loss tangent, dielectric constant. We showed you some data that shows how thermal conductivity is very important, as well as other parameters like conductor roughness. So thermal conductivity is the main control to manage temperature rise in RF materials. Additional considerations besides materials need to be taken, like the use of smooth copper or lower loss metal finishes, which were not covered in this video. Rogers offers additional material solutions to assist in the dissipation of heat from PCB surfaces, like a product cool span. This concludes this segment of the Road to 5G. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.